Hello, today we are going to be presenting the Caterpillar Parts Distribution Inventory Management Case Competition. My name is Cassie Pontfadia.
I'm Jack Lindquist.
My name is Annika Geiselhart.
And I'm Elise Warig.
And now we'll really quickly dive into the agenda just to give you guys a look into what we'll cover today. First, we'll start off with the case background and talk about what questions we have been asked to answer by Caterpillar. We'll talk about some of the assumptions that we made in the process of coming to our conclusion in this competition. Then we'll go through the data analysis and decision-making process that we took to come to our recommendation. And lastly, we'll cover key findings and recommendations with a detailed explanation of our analysis, additional things we considered, and our key conclusions. So to start off with the case background, Caterpillar was founded in 1925, and today it is a global leader in manufacturing, parts distribution, and service support. They value integrity, excellence, teamwork, commitment, and sustainability, and as a result, they're looking to improve themselves, specifically within the inventory management group within Caterpillar Parts Distribution, which is responsible for all 21 global parts distribution centers. Specifically, the IM Research Group identifies improvement opportunities, and this project will help them to assess certain changes and make the consequent determinations that they need to make to improve Caterpillar. These are the questions that we have been asked to answer in this case competition. First, we are finding the change in expected customer demand and change in stocking levels at the warehouse, especially in the next 6 months. Next, we are finding the plan for servicing this new potential demand. We will answer if stocking of new parts is needed, will we be increasing the inventory plan for stock parts that are needed, what the inventory investment will be upfront, and how this new demand will change inventory levels in the long term. Additionally, we will be talking about the data analysis and decision-making processes we used. Specifically, we'll answer how we decided which parts to add to the inventory, how we decided how many of those units to stock or add to currently stocked items, our method for balancing risk of lost sales, how the Our DSL List that has been given to us affected our analysis, how the currently stocked parts list informed our decision, and lastly, any impact and risks that we should quantify or consider and additional data that could have been useful to us had it been given.
Some assumptions that we made during this case were a 52-week working year, that we're only examining items that have been found to be replaced frequently on the same machines for customers in the past. Inventory policy is continuous review. There are 30 working days per month. Demand monthly deviation can be applicable across the population. Therefore, we do not need to calculate any sort of deviation based on the past 4 orders alone. The inventory holding costs and purchasing costs remain constant over time for each part, and many slow-moving parts are included in dataset. Our data analysis and decision-making process has 3 stages. In stage 1, we prime the data by creating a pivot table showing the average lifespan and usage hours of each part for each machine, sorted work orders by date, and determined demand for each part across applicable machines over the past 12 months. In stage 2, we calculated the new reorder point and economic ordering quantity. We did this by first converting average part lifetime by machine to number of times part would be replaced each year and each month. We summed number of part replacements across all machines, multiplied the number for new machines to aggregate annual and monthly change in demand. Next, we calculated average monthly demand and standard deviation per part, but only for applicable machines, based on past work order data. We then calculated revised average monthly demand by adding expected monthly change in demand to historical average. We calculated revised reorder point and EOQ values for all parts in the warehouse, and finally calculated both current and revised average inventory per part. In stage 3, we calculated practical changes to inventory plan. We first used the listed criteria to determine changes in inventory policy. This includes eliminating parts with no change in average monthly demand and eliminating parts with monthly demand less than 1 unit. Next, we determined a finalized list of 4,414 parts. We then calculated the expected change in customer demand and inventory levels in warehouse. We determined a plan for servicing new demand by calculating the number of new parts to stock and revised inventory plans for existing parts. Finally, we calculated the financial impact of suggested changes. Moving on to key findings and recommendations, our demand and inventory changes include a change in expected customer demand of about 42,746 units and a change in expected stocking levels of 44,701 units, which is about a 33% increase. As you can see, previous average stocking level was at 135,304.5 units, and our new average stocking level is 180,005.5 units. Our plan for servicing new demand includes that we do recommend stocking new parts at 3,365 units. We also recommend increasing inventory plan for 977 of our 978 parts that are already being stocked. 663 ROPs will increase by 19.45 units on average to 26.58 units. 977 EOQs will increase by 30.39 units on average to 59.22 units. Total inventory investment required is $2,366,652.53. Investment on currently stocked parts is $216,839.56. Investment on new parts is $2,149,812.97, and new customer demands will increase inventory levels in the long run.
So now we'll take a more detailed look at our approach and explain how we got at the results that Elise just presented. So to begin, as she mentioned, we started by creating a pivot table in Excel that found the average lifetime usage hours of each part when it was used on each of the three machines in question that the customers would be adding to their operations. So it found the average lifespan that each part had with respect to each individual machine. Using that, we converted that into a weekly number using the provided data, and then we converted that into the turns per year per customer machine, seeing how many times on average that inventory part would turn in the typical year per each customer machine that was in operation. We then multiplied that across the number of new machines that would be going into the operation, which was a total of 48 machines across the three types of models. And then we arrived at a yearly sum by adding those three figures together for each part to aggregate the demand for those parts. And then we finally divided by 12 to calculate the new monthly sum, since all of our data analysis would be conducted using monthly figures. This would give us this T sub M value that we're going to use in order to calculate things in just a few slides. Moving on, we then looked at the demand on a monthly basis using just the work orders we had available to us. We knew that the work orders only applied to the three models of machines that were looked at in the scope of our inquiry, so this wasn't a complete look at demand for each part, but it was a look at the demand for each of the parts with respect to the three machines that were going into service. So we were able to use a sum-ifs function in order to aggregate the demand for each of these parts in each of these months based on the work orders. As you can see, the historic monthly demand for the parts is provided for the three applicable machines, and we calculated it by summing the monthly demand for each part from the relevant work orders in each of the last 12 months, beginning in April of 2018 and ending in March of 2019. Since March of 2019 only had about a third of the month of work orders for it, we had to multiply those figures by 3 as an assumption in order to make sure that the demand was averaged out for that month. Next, we looked at calculating some things like the reorder point and the new EOQ that would be used for our calculations going forward here. So we'll take a little bit more of a detailed walkthrough of that so you can understand the math that went into our calculations. For the average monthly demand, we used a simple average calculation, summing up all 12 months of demand for each part and then dividing them by 12, as shown here. For the revised average monthly demand, we added the initial monthly demand that we got from the historic data, or D sub M1, to the T sub M value that we calculated in the previous slide, which is what we expect customer demand to change by for each part knowing now that we're adding 48 customer machines total to this dealer's assortment of customer machines. We then calculated the revised reorder point using the standard reorder point formula, which was to multiply lead time by the revised average monthly demand. In this case, lead time was provided to us in days for each part, so we needed to convert it to months, assuming on average 30 days in a month, in order to make sure all of our units matched. We then added that to kind of the buffer stock part of the formula, or the safety stock part of the formula, which involved taking the z-score that corresponded to the service level or the target service level in question for each part, multiplying that by the standard deviation in the demand we found for each part, and then again multiplying by the square root of the lead time. So L divided by 30 to the 1/2. And the 3 bullet points below that equation just spell out for you in greater detail what those 3 variables stand for. Next, we calculated the revised EOQ, or EOQ2, which we found to be pretty simple once you rearrange the equations. What we did was took EOQ2 over EOQ1, put the 2 equations over each other, and we were able to cancel out all the information that we assumed to stay constant, which included the purchasing cost and the holding cost, as we discussed earlier for the inventory. While we aren't sure what those are necessarily for each part, our assumption led us to believe that they would be the same across all the data for each individual part, but obviously differing by part. That gave us EOQ2, or the revised EOQ, equals the initial EOQ times the square root of the new demand divided by the historic demand average for each month. Finally, we looked at the average revised inventory and the average current inventory, which we could simply take by taking 1/2 of the EOQ that corresponds to each of them. So for the average revised inventory, we took 1/2 of EOQ2, and for the average current inventory, we took 1/2 of EOQ1. This model does assume that we're not holding any excess amounts of safety stock beyond what's called for in the reorder point and EOQ calculations. However, we believe it's pretty conservative given that most of the service levels were pretty high that we were targeting. So again, this slide here just takes a minute to summarize what we went through. Elise walked through it earlier, and I walked through it in pretty good detail, stages 1 and stage 2, so we won't cover that anymore here. But in stage 3, we did use the listed criteria to determine the changes in the inventory policy. So now that you've seen how we did it, we eliminated parts with no change in the average monthly demand, which was a lot of parts because not all of them were necessarily going to be employed on the machine, so obviously those were not going to be subject to our inquiry. And then we also eliminated parts with monthly demand less than 1, figuring that those work orders were either one-off work orders that didn't happen very frequently, or were just less important and not going to be demanded as frequently, thus not necessitating the need of holding extra stock there. Again, this led us to our finalized list of 4,414 parts, from which we calculated the expected change in customer demand, determined a plan for servicing the new demand through these calculations, and calculated finally the financial impact of the suggested changes. Now Annika is going to walk you through some of the additional considerations we undertook when going through this process.
Okay, so now I'm going to take a little bit more of a deep dive into the additional questions that were posed to us in the case. So first, I will address balancing the risk of lost sales. So as Jack kind of touched on a little bit earlier, we recommend a more conservative approach in order to mitigate loss of sales by building initial safety stock to counter uncertainty in demand for these additional 48 vehicles that are being added to the fleet. So there is the potential to recover this storage and capital cost over the unrecoverable loss of sales if we do not stock these parts initially. Additionally, if further cost savings would like to be achieved, we would recommend eliminating some parts with the lower target service levels. So for example, a great many of these parts that we recommend you stock have a 60% target service level. If those are eliminated, then the capital investment will be reduced to $225,166, and the stock parts will go down to 1,106 parts. The second question that was posed to us was the implications for the RDSL list. So parts included on the RDSL list were prioritized within our group on the final stocking list. There were no limitations given in terms of budget or stocking limit within the warehouse, which is why we chose to incorporate pretty much all of these RDSL part numbers. Again, we assumed a more conservative approach to prevent the loss of sales and protect these high service levels against uncertainty in demand from large increase in the customer machines. So the parts that would have initially been excluded using our rejection criteria that Jack talked about earlier were brought back if they were on the RDSL list in order to ensure all critical components are in fact stocked. And if not all RDSL parts can be stocked, fast-moving and shutdown parts should be prioritized over the slow-moving or those parts less integral to the operation as they are on their own kind of critical to recommended criteria levels. Moving on to currently stocked parts. So currently stocked parts were initially explored to understand which parts were deemed most critical for these dealers to stock. Our analysis ensured that parts currently stocked for the machines in question would remain stocked in the revised model. However, we did not disqualify any parts that were not currently stocked if demand for them was expected to increase following the introduction of these 48 new customer machines. And revised monthly demand was the key consideration in this situation. And here are just some other considerations throughout the project. So for impacts and risks, once again, there was no limit on warehouse capacity or budget for this initial capital expenditures. We do understand that our strategy was the most conservative. However, we feel as though we presented a few different options for Caterpillar if the capacity or the budget was too high. Additionally, the assumed RDSL parts should be reordered in the RICO quantities as they were typically ordered in that fashion, so just to maintain the service level that was there. Additionally, the method for determining the revised EOQ is subject to very many assumptions, which may not necessarily hold true over time, some of which included the constant ordering and holding costs, and we were not entirely sure about the accuracy of the listed initial EOQ, especially for just a very few parts in our original analysis. And then the parts with monthly demand less than 1 were given lower priority, which could be problematic if these parts do end up being critical to the operation. And then any additional and useful information that we could have had would be more accurate initial EOQ values, information about the RDSL parts that were not included in the part data, as a very many, I think about 70 were not included in the part data sheet initially, and then we would have liked to have had the ordering and inventory costs in order to make our EOQ more exact. So once again, here you can see our key conclusions if you would like to take a minute here to pause and reevaluate them. So because we employed a conservative approach in our analysis, you can see that we anticipate inventory levels and investment to increase fairly substantially in the next 6 months. However, we believe that this investment is necessary to ensure high service levels that will satisfy customers. As a result, the required investment will be financially worthwhile and earn itself back in the long run. Thank you so much, and we welcome any feedback that you may have, and upon request, we will be more than happy to provide any clarification or analyze data.